Welcome to another Essential Explainer. Today, we are taking a massive, highly strategic journey through the world of electricity. Now, if you're studying for your Cambridge physics exams, specifically looking at syllabus codes like 9702, 0625, or 5054, you already know that electricity is a cornerstone topic. It is everywhere. We interact with electrical components every single day, but to secure those top marks, we have to look past the wires and the switches. We need to know exactly what is happening down at the subatomic level and how that translates to the numbers on your voltmeter. So today, we're not just reading textbooks. We are going to completely demystify electricity, starting all the way down at the microscopic level of the electron and building right up to the macroscopic everyday components you'd find in a circuit. We'll be using some incredibly clear, structured visuals to guide our understanding and lock in that knowledge. Get ready to see the invisible forces that power our world in a whole new light, and more importantly, learn exactly how examiners want you to write about them.
Okay, let's dive right into this and look at our roadmap. We have a systematic approach today. Section 1 is basic terms and the truth about current. Section 2 covers defining potential difference and power. In Section 3, we'll tackle the math of the macro. Section 4 is all about component IV characteristics. And finally, Section 5 wraps up with resistivity and Ohm's law. Let's get to work.
Section 1. Basic terms and the truth about current. Let's unlock the fundamental flow of charge.
Let's start with the absolute foundation. When we talk about an electric current, what we are really talking about is the flow of charge carriers. In your standard metal wire, those charge carriers are electrons. And here's a critical concept examiners love to test. This charge is quantized. That means it is bitty. It comes in distinct, indivisible packets. You literally cannot have half an electron flowing through a circuit. It's an all-or-nothing deal. But look at the screen right now and notice this massive, almost unbelievable contrast in speeds. This is a classic trap in multiple-choice questions. When you flip a light switch, the light turns on instantly, right? That's because the electromagnetic signal, the current front, moves at nearly the speed of light, which is 3 × 10⁸ meters per second. But the actual physical electrons, they are not zooming along at light speed, not even close. They move with a drift velocity of only about 0.1 millimeters per second. Think about that for a second. That is literally slower than a snail. Why are they so sluggish? Because a metal wire isn't an empty tube. It's a dense crystal lattice of vibrating positive metal ions. The electrons are constantly colliding with this lattice, bouncing back and forth, losing kinetic energy, and only slowly drifting forward in the overall direction of the current. They're basically playing the world's most crowded game of pinball. Keep this picture in your mind because it is the secret to understanding resistance later on.
Now, to measure this incredibly important flow of charge carriers, we use the ampere. The ampere is our base SI unit for current. If a question asks for base units, you give them amperes, not coulombs. The ampere is strictly defined in terms of the number of electrons passing a specific point in exactly 1 second. And this directly leads us to how we define total charge. Charge is a derived quantity measured in coulombs. 1 coulomb is simply defined as the amount of charge that passes a point when a current of 1 ampere flows for exactly 1 second. So if you want the formula, it's straightforward. Charge equals current multiplied by time, or Q equals I times T. If a 3 ampere current flows for 10 seconds, 30 coulombs of charge have just moved past you. It's that simple. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
And this image right here brilliantly illustrates exactly how we calculate that current based on the physical properties of the wire itself. This derivation is gold for your structured paper. Look at the cross-section labeled A. In a given amount of time, let's call it t, each individual charge carrier travels an average distance equal to its drift velocity v multiplied by t. So if we want to find the volume of that shaded section of wire where all the moving electrons are, we just multiply the cross-sectional area A by that distance vt. So the volume is A times V times T. Now, if we know the number density, which is the number of charge carriers per unit volume represented by N, and we know the charge of each individual carrier, Q, we can find the total charge in that chunk of wire. We multiply volume by N by Q. But remember our definition of current. Current is total charge divided by time. When you divide that massive expression by time, the time variable elegantly cancels out. And what are we left with? We are left with a beautiful, highly testable equation. Current I equals A times N times V times Q. I equals ANV. It perfectly links the microscopic sluggish drift velocity of those electrons to the macroscopic current that we can actually measure with an ammeter.
Let's move on to Section 2, defining potential difference and power. We know the charge flows, but what are the macroscopic driving forces behind the flow?
So we've established that charge flows, but why does it flow at all? It doesn't move on its own. The driving force pushing those electrons through the wire is the potential difference, which we measure in volts. If you are asked to define potential difference in an exam, you need to be extremely precise to get the mark. You can think of potential difference as the energy transferred, or the work done, per unit charge. Specifically, a potential difference of exactly 1 volt exists when exactly 1 joule of energy is transferred as 1 coulomb of charge moves from one point to another in a circuit. It's the electrical pressure. It's the push from the battery that gets those electrons drifting through the dense metal lattice we talked about earlier. No potential difference, no push, no current.
Now, as that energy is being transferred to push the charge around, we need a way to measure the rate of that transfer. This is where power comes in. The unit of power is the watt. 1 watt represents work being done, or energy being transferred, at a rate of exactly 1 joule per second. Let's put this into perspective. While the volt tells us how much energy each individual packet of charge is carrying, the watt tells us how fast that energy is being utilized by the component. This is exactly why your electricity bill at home is based on power. The power company doesn't just care about how many electrons moved, they care about how fast your house is consuming their energy. A 100-watt bulb transfers 100 joules of electrical energy into light and heat every single second.
But here is the catch. The circuit doesn't just let all that energy flow perfectly freely. The materials physically push back. This opposition to the flow of charge is called resistance, and it's measured in ohms. A component has a resistance of 1 ohm when a potential difference of 1 volt across its ends produces a current of exactly 1 amp. Think back to what we discussed in Section 1. Remember those electrons playing pinball, constantly colliding with the vibrating positive ions of the crystal lattice? That physical interaction, those microscopic collisions, are the root, fundamental cause of electrical resistance. The more they collide, the harder it is for the current to flow, and the higher the resistance in ohms.
Section 3, the math of the macro. So the crucial point is how we bring all these definitions together into workable mathematical relationships.
Take a screenshot of this slide right now, because this is your perfect, clean study guide of foundational definitions. We have charge is current times time. Voltage is work over charge. Power is voltage times current, and resistance is voltage divided by current. But look closely at what happens when we start combining these. If we substitute the resistance equation into the power equation, we unlock 2 incredibly vital new formulas. Power equals voltage squared divided by resistance, and power equals current squared times resistance. Why do examiners want you to know these? Because depending on what information they give you in a circuit diagram, these variations allow you to calculate the power dissipation instantly. If you are in a series circuit where current is constant, use P equals I squared R to compare components. If you are in a parallel circuit where voltage is constant across the branches, use P equals V squared over R. Knowing which equation to pick saves you massive amounts of time on the exam. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Moving right along to Section 4, Component IV Characteristics. We're going to look at how different materials react when potential difference is actually applied across them.
Not every material behaves the same way when you crank up the voltage. This is a prime area for long answer questions. Look at the graph for a standard metal wire on the left. It's a perfect straight line passing straight through the origin. The current is directly proportional to the potential difference. What does that mean? It means its resistance is perfectly constant. It's an ohmic conductor. But compare that to the filament lamp next to it. As the voltage increases, the line starts to curve and flatten out. The current doesn't increase as much as you'd expect. Why does this happen? Examiners love asking this. Let's break it down logically. A tungsten lamp filament heats up incredibly fast, reaching around 1500 degrees Celsius. At these massive temperatures, the positive ions in the metal lattice vibrate much more violently. Because they are swinging wider, they present a much larger collision cross-section for our drifting electrons. This causes more frequent collisions, which drastically reduces the electron's drift velocity. And as we know, lower drift velocity means a drop in current for the given voltage, which means an increase in resistance. The physics of the heat literally changes the electrical properties.
But wait, it gets even more fascinating and slightly counterintuitive when we look at semiconductors. Components like thermistors and late-dependent resistors, or LDRs.
They behave exactly opposite to metals. In a metallic thermistor, as the temperature increases, the added thermal energy actually does something special. It frees up more mobile charge carriers from the atoms themselves. Because there are suddenly so many more electrons available to carry the current, this effect completely overpowers the increased lattice vibration, so the overall resistance actually decreases as it gets hotter. Hotter environment equals lower resistance. The exact same logic applies to LDRs, but instead of thermal energy, it's light intensity that's doing the work of freeing the electrons. Brighter light equals lower resistance. And then we have diodes. Think of diodes as the one-way valves of the electrical world. They block current almost entirely in one direction. That's called reverse bias. But in the forward direction, they require a specific set potential difference, usually about 0.6 volts for a silicon diode, before they suddenly turn on and conduct with very little resistance.
Finally, Section 5, Resistivity and Ohm's Law. We are going to conclude our macro journey by looking at the specific, inherent physical properties of the materials themselves.
You have undoubtedly heard of Ohm's law before, but in Cambridge exams, being close isn't good enough. Let's read the formal definition carefully. The current through a metallic conductor is proportional to the potential difference across the conductor, provided the temperature remains constant. I want to heavily emphasize that last part. As we just saw vividly with the filament lamp, if the temperature changes, the resistance changes, and that beautiful proportionality breaks down entirely. Ohm's law is not a universal law of nature. It only holds true under constant physical conditions. If a question asks you to state Ohm's law and you forget to write provided temperature remains constant, you will lose the mark. Period.
So, assuming we do have a constant temperature, what actually determines the baseline resistance of a wire? It comes down entirely to its physical geometry and the specific material it's made of. Let's build the formula. Step 1. Resistance is directly proportional to length, represented by L. Think about it. A longer wire means a longer journey, which means more vibrating lattice ions for the electrons to collide with. Longer wire, higher resistance. Step 2. Resistance is inversely proportional to cross-sectional area, represented by A. A wider wire is like adding more lanes to a highway. It provides a wider path, easing the congestion and allowing the flow to happen more easily. Wider wire, lower resistance. Step 3. We combine these geometric factors with a constant of proportionality called resistivity, represented by the Greek letter rho. Resistivity is an inherent property of the material itself. Copper has a completely different resistivity than tungsten or nichrome. Putting it all together gives us the master formula. Resistance equals resistivity times length divided by area. R equals rho L over A.
Let's look at a practical application of this, because this formula is guaranteed to show up in your practical papers, Paper 3 or Paper 5. Let's say you are calculating the length of nichrome wire needed to build a heating coil, and you need the cross-sectional area. Here's the catch. You cannot measure area directly. It's a derived quantity. In a real lab setting, you would use a micrometer screw gauge to measure the diameter of the wire. And here is a crucial practical skill that examiners look for in your methodology. You must measure the diameter at 3 different points along the length of the wire and take an average. You do this even if the readings look identical, because manufactured wire might not be perfectly uniform. It might be slightly stretched or flattened in places. Once you have that reliable average diameter, you have it to find the radius, use pi r squared to calculate the cross-sectional area, plug that area into our R equals rho L over A formula, and finally solve for your required length. That is exactly how you secure maximum marks on an experimental design question.
I want to end with a provocative trick question to really test your grasp of these concepts and to see if you can think like an examiner. Imagine you have a standard copper wire. You pull it and stretch it out so its length increases, but somehow, magically, its cross-sectional area stays exactly the same. We know from our formula, R equals rho L over A, that because the length went up, its overall resistance will definitely increase. But what happens to its resistivity? Think about it for a second. The answer is absolutely nothing. There is no change. The resistivity remains exactly the same. Why? Because resistivity is an inherent, fundamental property of copper at a given temperature. You changed the physical geometry of the wire, but you didn't change what the wire is made of. Understanding the difference between a specific component's changing resistance and a material's constant baseline resistivity is the absolute key to truly mastering electrical physics. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams, your Cambridge success starts here.